So the other time, like we said, we actually look into the made up of the paper. So the first week was the summary. The second week was we look into the paper in deep, part one, that is preemptive diagnosis of Alzheimer disease in the Eastern Province of Saudi Arabia. So, and I want to believe we've discussed the introduction, the review of literature. We went through the methodology, the materials and methods, so the procedures, and made us realize what what are the important information that you need to put in your material method or in the experimental description. And we summarize it as anything that if you don't provide it, people cannot know how you have done your experiment. Those things become very compulsory for you to provide. See, any information that someone can just Google and find online, you don't need to put there, like how to install Weka, how to work with Python. This is not for discussion in this kind of report. Anyone want to learn Python or want to learn Weka can do it elsewhere. So you tell us information about your experiment that if you don't tell us, we cannot reproduce your work. Because one of the very important aspects of research outcome is you need to make it so clear that someone can just sit down on his computer or our computer and reproduce what you have done. And that will give a lot of credence to what you are presenting as outcome of your work. So we look into the material. We also even look at the framework that was proposed. And we said it's very good if you can represent your framework in a very nice flow chart that will show the flow of information. So this will add more to the experimental description you have made. But most importantly, you must not forget to mention the platform you use, very important. Of course, the algorithm and the hyperparameter of those algorithms. And how did you divide your data? You see, data partition, very important. Is it hold out method like 70% for training, 30% for testing, or 70% for training, 15 for validation, and 15 for final testing? Or is it cross-validation, tenfold or five? Even if it's cross-validation, you cannot just tell us cross-validation because there are several types. Is it fivefold? Is it threefold? Is it tenfold? So you need to be very specific. These are very important information that must appear in the description of your experiment. Otherwise, such reports, such research risk being rejected in the community of researchers, because you are leaving so many things for people to start making guess, which means it doesn't guarantee that they are going to be able to reproduce your work. And any work that cannot be reproducible, then it should be automatically rejected in any standard research house, like journal, even conferences. If you cannot reproduce your work, then what is the essence of submitting it to a journal? It means there's no even guarantee that you have even done anything. See? So this is very important. We also look into that data description that day. And then we also look at the data preprocessing, outlier removal was done, and missing value imputation was done. And I mentioned to us there are several types of outlier treatment and also missing value treatment. And I made it clear that outlier is more difficult to identify compared to missing value. When you look at your data, you can easily see that, oh, there's a missing value here. Either there's going to be a none, not a number error, or you're going to be a question mark, or the place is going to be empty. However, for outlier is a number, but that number is out of range for that particular column. So, and what is out of range for a column might not be out of range for another column. So that is why it's not easy to identify outlier in your data set. So you have to use things like box plots and also other tools to identify them. Because you see, and in age, if you are, maybe I'm modeling my student, there's a student predictive solution. Under the age, I found out that the student has like 70 years or 90 years or 120 years. How can somebody be 120 years and be an undergraduate? I will know that something is wrong with this number. But in the second column or another column, maybe weight, you can see somebody who is 120 kg and is not an outlier. So what is outlier in one feature might not be an outlier in another feature. So that is one of the reasons why outlier is very challenging to detect. Once you are able to detect outlier, the same method used for missing value treatment can easily be used to treat the outlier detected, either by replacing with the mean. The best is to go back to the original source and get the original data from where it was brought to you. But this is not always possible in most cases. Maybe the company or the hospital doesn't even have, it has been entered how many months ago? They cannot even locate the original value. They are not even aware how 120 came to be in the age of those students. Editing can be represented. Maybe they were trying to type 20 and mistakenly the keyboard pressed 1 before 20. These are some of the sources of outlier that comes to our data set, and we face it on day-to-day activity. So we need to know how to handle them. So these were all handled appropriately. And I remember also I mentioned last time that when you use missing value treatment method, that investigating which missing value treatment is going to work for us is a big task. So you have to choose the one that you can, I think this one will work for me, hopefully. Because if you want to investigate all of them, then you have to spend a lot of time. That's the mean value, there's the median value, there are so many using the common value to replace the missing value, and so many other methods of missing value treatment. And we did refer us to our earlier video on missing value treatment and outlier detection, how you can treat these outliers. Now, so then we also discussed about the data scaling. That is that sometimes you might need to sometimes you might need to minimize, normalize your data. That is, especially when the features value are different. The range of features are different from one feature to the other. So normalizing them to be in the same range might make it easy for the machine learning algorithm to be able to understand the data better. So, however, if you normalize your output, usually output, personally, I don't encourage people to normalize outputs, especially in regression. In classification, you don't need to normalize that because it's either 0 or 1 or number of classes. However, for regression, some people do normalize their target, but if you normalize target, you have to remember to denormalize the final prediction before you conclude your work. This is why people usually avoid normalizing the output. You can normalize the features as the case may be. So having discussed that last time or so, then we look into some of the algorithms that were described, and I mentioned how we need to tell us a little about your algorithm and link it to the present work that you are doing. Yeah, finally, we also mentioned how smooth was used, that is the synthetic minority oversampling, because the data is imbalanced. So they use smooth. You can see how they have the original. See, with the original, you can see the original data, and then you can see the oversample method, the original, the oversample, the original, the oversample. So they were able to see that, okay, the oversample method seems to be doing fine, as the case may be for some of the system. Especially we're going to mention. So why SVM was preferred over other methods, because at the end of the day, they were even k-nearest neighbor, which is a very simple algorithm, was performing closely to that of SVM. Then why did we settle for SVM? We're going to discuss that once also today. So today we are looking into, starting from where we stopped, which is establishment of the Alzheimer's disease prediction model. Now, having done the necessary pre-processing here and there, then we need to now finalize and produce the final model. And it has been decided that the oversample data is going to be used. Now, in the establishment of the final model, you need to let us know the performance measure. How do you want to judge the performance of your model? This has been made clear here. You can see the precision, the recall, accuracy. All these are usually provided when you run your model, when you build your model. So we are going to analyze it. Now, Well, we know the true positive indicate the instances that are classified with AD correctly. That's true positive. See, why false positive represent the instances classified with AD incorrectly. So false positive means somebody is not sick, but the system predicted it to be sick. While true negative, there are those that are not sick and they are correctly predicted as not sick. Then the false negative represent when someone is predicted to be free of AD, but meanwhile the person is sick. And in medical, false negative is a serious mistake. It's a very, very serious mistake because the system will predict that someone is good. He will continue to think that he's good actually, and later will develop complications. We don't want this. That's why we pay attention to systems that make mistake. If the system is making mistake on false negative, it's very serious. We rather get or select an algorithm that is getting lesser accuracy, but the mistake are coming from the other side. False positive. False positive means you are saying someone is sick, but the person is not sick. You go to the clinic for follow-up, or further tests will reveal that the person is not sick. So this is still okay. Of course, we don't want any mistake. You see, any error is bad. We don't want it, either false positive or false negative. But sometimes when you have, as they say, two evils, you look at the lesser of those evils. You see, telling someone that you are sick, meanwhile you are not sick, is not good, because that could cause panic. Yeah. But however, once he made follow-up in the clinic, they would declare him that, oh, we are sorry. It seems the machine learning system mistakenly predicted you to be suffering from this disease. We can conclude that you are free of this disease. At least the person will be happy. At least, although he was maybe panicked initially, he will be happy finally after being exonerated from having that disease. But let's look at the reverse case. When someone is predicted to have not to have Alzheimer disease or any disease predictive solution, only for the person to actually develop chronic aspect of that disease or run into complications, and they say, oh, it seems they missed this prediction. It happens every day, by the way. So that's why in medicine, the effect of false negative in the medical profession is more than the false positive. That is why when you have it, we select the one that is having lesser number of false negative, because it means it's going to be having mistake with lesser evil or lesser consequences. Now the model that we also mentioned, we're going to talk about under the result discussion. So apart from one of the things that was carried out actually is the feature selection, because you can see here the performance is still a little bit low, 92, 93, 87, 88, you see 90, 91, but consistently it seems the oversample method, the oversample data is getting better result than the initial one. So next thing that was done was to carry out what we call the feature selection. You see, feature selection play a vital role in reducing the computational power of building models. One of the advantages of feature selection is it reduces the computational power needed to achieve your result. But the most important one is that it has the possibility of increasing the accuracy, as we are going to see. You see, the moment feature selection was implemented, so you are going to see that most of the model jump up from 92, 91 to getting 95. You can see 95.56, 95.52, from 90, even some from 88 jump to 94 because of feature selection. Because we had a video where we explain the cost of dimensionality. Cost of dimensionality is a serious problem in machine learning, whereby the number of samples needed to work with the appropriate feature increases exponentially. If you have one feature, for example, you need 10 samples. When you have two features, you need 10 raised to the power 2, which is 100. So when you have three features, you need 10 raised to the power 3, which is 1,000. Imagine having 25 features. Here, 1, 2, 3. The original feature was like 18, we mentioned last time. So we are supposed to have 10 raised to the power 18 samples. But we told you we have only 152 samples. because samples are usually limited in number. You cannot increase it because the data is just not there. So feature selection, when you reduce the number of features, there is possibility that you get better result because of the cost of dimensionality. But the more the number of features, the more the number of samples you need, but the samples are not there. So the only solution is for you to reduce the number of features so that the little samples you have can cope with the implication of those features. So here, the special sequential forward feature selection was utilized, in which case each algorithm is made to select the feature that work for it. This is a special case of feature selection. You see, if you push in the algorithm supplied with the data, it search through and try to run experiment. It's a very simple method of implementation. What basically you do is, it's like you're starting with feature 1. See, you run the experiment using only the feature 1, the gender. Then you add age to it. You see, then you add pulse to it. You keep doing, increase it gradually. So as you go forward, that's called sequential forward feature selection algorithm. So someone might want to look at what of the backward, what of the hybrid? You see, what of hybrid? There's still room to actually explore the hybrid feature selection, whereby as you're adding it, you're also removing. As you're adding, you are removing it. You see, it's an exhaustive search technique. It do work, but it takes a lot of time. So in this case, the sequential forward feature selection has been used. And to investigate, one of the topics that could be next on the agenda for this kind of paper is investigating the effect of feature selection types. So you want to use different feature selection and see which one is going to work for you. That is because we still have very big room for research update. In this case, 95.56 is the maximum. We are going to 100. And the one that got the best actually is achieving with 13 features. That's still huge to me. Imagine you want to run machine learning model for patient and you ask all of them to go and do 13 medical tests. To me, that is still very high. Can we still bring it down to like very few medical tests, 5, 6, 3, as the case may be? So there's still more work that needs to be done. We need to explore other feature selection algorithm, but like you know, research always have a defined bound, time bound. So you have to select appropriate thing. This is the first time anyone is working on this data. 95.5C is not bad for a start. Considering all effort that has been made to push it up, this is why it can start. So the next is to now say, okay, how can we push it up? Can we bring down the number of features? Personally, I'm interested in bringing down the number of features. For k-nearest neighbor, the very simple algorithm, we can see that it has just only 6 features, which is very interesting. And it's competing with the best guy at 95.52. So to me, they need to have a lot of discussion on these. You see, with 6 features, 95.52, I better go for this. Why this difference is very minimal, but you are going to see later why we chose to go for support vector machine. You see, it has to do with the false negative and false positive I analyzed earlier. Now, because this is doing really great, with 6 features, less than half of this is getting 95.52. So we have other boost with 10 features getting this, and edge boost with 6 features, so getting lesser than the k-nearest neighbor. This is why I mentioned at some of our lectures in the past that we should not underrate the power of simple algorithm. Who can ever imagine that KNN, as simple as it is, can compete favorably well with these are very sophisticated algorithm. XG boost, ADA boost, but the ADA boost is an ensemble. But yet, this is comparing even better than it actually. So that's why we always recommend start your modeling with simple algorithm, k-nearest neighbor, decision tree, SVM, and then you go up as the case may be. So having done the feature selection, now what involved, this is just a little the algorithmic presentation of sequential feature selection for those who like mathematics. So we can see there of even algorithm procedure, you can write a code for that. Now, Having said these are the final performance that has been established by the system. You can see we have the accuracy, we have the precision, we have the recall. Now, so you can see the difference is going to be here, where we're going to have it, recall as the case may be. Now, so we also mentioned the optimization strategies, which is very important. You have to optimize. We mentioned also earlier. So it told us here the range of values they have searched for KNN, SVM, and others. If you don't optimize the hyperparameter, you are not being fair to each of the models. You need to look for the hyperparameter that work for each of the model. Then that's where you can compare them appropriately. Now, so now having said that, the next thing very important before we go to finally the conclusion is when you are discussing your result, this is very important. This is what we call confusion matrix. Confusion matrix. You can see the confusion matrix for each of the models. This is, you can see here, this in dark, we can call it dark blue, yeah. These are the correct classification. 87 samples were predicted to be AD, and they are correctly AD. Prediction, these are the original. This true label, and then the predicted value like this. So 83 people, they don't have the disease, and they are correctly predicted as not having the disease. So this is called true positive, true negative. Now, this is called the false negative. First, because you can see here, this is true label. Everybody here, they are having AD. 87 plus 2, they are like 89 people having this disease, AD. But out of this 89, 87 have been predicted to have AD, while 2 mistakenly predicted not to have the disease. You can see non-AD. This is colon for non-AD for prediction. So you look at it this way. These are the true label. Everybody here is AD. They are supposed to have that disease. However, our model predicted 87 as having it and 2 as free from it. This is a mistake. We call it false negative. Let's pay attention to that. In medical, it makes a big difference. And that's going to be the basis for deciding our final results or the final model to be selected. And here is false negative because everybody here that's supposed to be non-Alzheimer disease patient. This 83 plus C, that is 89 also. See, all the 89 here are supposed to be non-AD. However, 83 of them are predicted to be to be free, and 6 were predicted to be having the disease, even though they don't have any disease. So this is false positive. That is, you are predicting him as positive, meanwhile it is false. It's not correct. Now, there are 2 mistakes types, false negative and false positive. So SVM is having 2. Why for the false negative? And we already explained that false negative is a no in medical. False negative means someone who is sick, you are predicting him as not sick. So you go home and develop complication. We don't want it. We don't want this one also, but we can afford to manage this. So they're saying, okay, you're having this disease, you go to the clinic, they double check and they say, oh, congratulations, you are free. I think this is better than this one. This is an interpretation. Now, for K-nearest neighbor that has been closely competing with SVM, you can see that K-nearest neighbor also had false negative 3. You see, 3 people against 2. But for this one, it has only 5. This one had 6. You can see that the mistake here is more than the mistake here. Why the mistake here is lesser than this, but this mistake is more costlier compared to this mistake. So that's why we go for someone that has lesser of this serious mistake. And that's why we selected SVM, because these are the 2 that are closely related. Just one difference, yeah. Now, let's go down. You can see for other boost, 5. See, the mistake here is total of 8. Here also is total of 8 because they're almost having the same accuracy as you can remember, 95.5. Now, when you look at this is 9. Unfortunately, 5 of them are coming from the serious mistake, which is false negative. For the XG boost, 10 mistakes, 4 of them coming from this area, Majority come from this side. So even though XGBoost has lesser accuracy compared to other boosts, if we want to rank model, we will still prefer this guy over this guy because the number of false negative is too much here compared to this. So we go for the one that is having lesser number of false negative, which is support vector machine 1. Then 2 is going to be K nearest neighbor, then followed by other boost, then followed by XGBoost, based on the implication of the mistakes they are making. Now, however, like I said, there's very room, it's just the beginning of this research work, very big room for better improvement. I'll personally be interested in looking into K nearest neighbor, since K nearest neighbor is having just only 6 features, and this one is having 13. Can we do something to do more rigorous feature selection? And hopefully maybe K nearest neighbor might be able to get us even better result, or maybe SVM also will improve over time. But for sure, these are research for the future. Like I always say, research must be time bound. Otherwise, you never finish whatever you are doing. You cannot do, as you are going in research, you keep noticing some things, but you have to be documenting them. This should form part of your recommendation for future work. Other people can benefit from it. You don't need to finish everything at a go. Otherwise, you might not have the opportunity to finish it. And finishing research and communicating to the international world, to the international community of researchers, to let them know there's an opportunity here is one of the advantages of having early result or outcome to be sent out. And that is the essence that when you are defining your research proposal, it has to be time bound. It should be something that is achievable within a specified time. Because like I told you, we talk about even to do the oversampling, there are different methods to use. To do missing value treatment, there are many methods to use. To do outlier treatment, several methods. Even feature selection, several methods. So if you have to do everything in the same work, you are not going to finish. And that's not a good attribute of a research. So that is why you do what is acceptable while following the normal procedure, while then the next opportunity for the other people, either your team or another team, they can take it up from there. So finally, because of this analysis, support vector machine was selected to be the best among all the models. Why? Because it achieved the highest, the least false negative in the committee of the method that has been used. So, and then others are further discussion. You try to discuss your result. What we are doing now is discussion of result, by the way. You have to analyze. So why SVM has to be selected over KNN? You have to tell us the implication of 2 and 6, because for somebody who is just looking at it, you say, but 3 is close to 2, but this guy is having 6 features. This one is having 13 features. From feature selection point of view, KNN should be the best for us. However, we cannot ignore false negative in medical. If it were to be another area of application, then we'll be saying another thing entirely. You see, or if it is production system, false positive is what they don't want. False negative is acceptable. But for medical, false negative is a no. So whatever method that is giving you acceptable accuracy with very low false negative, we go for it. And that is why support vector machine has been selected, even though there's room for improvement in future to see that the 13 features that is being used presently could be improved or increased, or reduced to the barest minimum, so that when we want to gather data for the medical test, it will be cheaper for people to get it, and to be easier also to collect the medical test. Is somebody doing 13, if we can do just 3 or 4, that would be really great. That will encourage the population to embrace this kind of medical intervention systems. So further results, we have further discussion of results. You see, when you are doing further discussion of results, if there is anyone that already work in this area, you can present their results in this section and you can compare your work with them. However, this is the first time any work is being done in this area. So they just do further analysis of the results. So telling us the percentage improvement. See, when you are discussing your result, you don't need to just repeat what you have in the table. You see, you can tell us the percentage improvement that SVM provided over KNN, and then tell us why the false negative rate that is very low is the yardstick for selecting SVM as the best model. Then this is called area under the curve, ROC. It's another way of showing the result of classification. Any machine learning platform will plot it for you. You see? So what we are looking for something perfect like this that will go up and then you see it here. See? So you can see that each of them, non-disclosure, but SVM actually display that it could be, yeah, this is SVM ROC. See, area under the curve. So they are all closer together. As you can see, this one is a little bit lower compared to that. So, however, the first negative, the first positive, they're very, very important when you are analyzing results of from medical application of machine learning. So, in conclusion and recommendation, we said this project was undertaken to develop a machine learning model that preemptively predict Alzheimer's disease to enhance the prevention procedures and decrease the mortality rate induced by the illness. So the idea is if we can get people right before they actually fall sick, so why don't we do that? We have the technology now. Unlike before that, by the time people complain about something, it's already too late. So this is the idea. So current future work actually may include investigating approach to reduce the number of fissures. You see, I told you. So we have recommended here that future work may include investigating approaches to reduce the number of fissures while maintaining high accuracy and recall. You see, so the recall is the one that is talking about the first negative implication. And then also, we want to investigate even better way to model the missing value treatment and also of order. So he said the experiment can also be expanded to address other chronic disorders. And moreover, it is recommended to use the least computational techniques and data set available while experimenting with medical problems. That is the algorithm that will consume least computational ability characteristics or needs. So this is our recommendation. This will facilitate adapting the preemptive prediction tools in most healthcare facilities while addressing the economic concern. See, the idea is that if you can do feature selection, because for me, the support vector machine that needs 13 features is economically not viable, because if you have people to do 13 medical tests or 11 of them before they can use the system, that's going to impose a lot of financial burden on the people and can discourage them from embracing it. So we rather recommend that future work should look into reducing the number of features while increasing the recall. That is, false negative should be brought down even to 0 where appropriate. So that if there's going to be any mistake, it should be from the other side, not the first negative. So this is what we're going to have for this. So give room for question and any clarification that might be needed. So thank you very much all for listening. So I think that is the end of that particular of this presentation of our paper presentation demos, where we demonstrate different papers. So thank you all. So we can raise up our hands so in case we have any question or clarification to make. Thank you all very much for listening and wish you all the best. Thank you.